Video will delve into whether a rope extending from the International Space Station could enable humans to climb into space. Key elements influencing this possibility include orbital mechanics, gravity, and material science. The ISS orbits Earth at an altitude of approximately 400 kilometers and experiences microgravity due to its constant freefall. Objects in orbit need to maintain specific velocities, otherwise they face re-entry or risk drifting away. As depicted in the image, various scientific domains such as energy dynamics also play a crucial role in understanding this complex problem. Let's explore these factors to see how they impact the hypothetical climbing scenario. Continuing from our exploration, let's focus on the dynamics of a tether in orbit. Due to the orbital motion of the ISS, the tether would not hang vertically towards Earth. Instead, it would experience tension from two opposing forces, the outward centrifugal force and the inward gravitational force. This creates equilibrium challenges, as depicted in the image by the red arrow showing the centrifugal force and the blue arrow representing the gravitational pull towards Earth. Climbing the tether would demand energy to overcome these forces and align with the orbital velocity of the ISS, which is around 7.8 kilometers per second. Additionally, if the tether were stationary relative to Earth, it would hinder ascent by adding challenges like atmospheric drag and gravitational pull. This intricate balance highlights why a straightforward climb from a tether poses significant difficulties. Building on our previous discussion, let's consider the structural and material challenges of maintaining a tether extending from the International Space Station to Earth. The illustration highlights the immense tensile strength required, far beyond what current materials can provide. For example, while materials like steel and Kevlar have strength ratios of 30% and 50%, respectively, even carbon nanotubes, which reach up to 80% strength, fall short of the theoretical limits needed for a tether this length. Moreover, dynamic stresses, including atmospheric drag, tidal forces, and vibrations, pose significant threats to the tether's stability. The image indicates these stresses with arrows, emphasizing the complexity of maintaining structural integrity. Additionally, the downward pull of the tether will lower the ISS's orbit, necessitating continuous energy input to counteract this effect. These formidable challenges underline why current technology cannot yet support such an ambitious endeavor. Exploring alternative concepts, we find that a space elevator involves a theoretical tether anchored to Earth's equator, stretching beyond geostationary orbit. However, given the ISS's lower orbit, this idea doesn't apply. Rotating skyhooks present intriguing engineering possibilities, yet face significant technical hurdles. The image illustrates this by highlighting skyhook challenges and marking the ISS tether as physically impossible due to insurmountable energy needs and material limitations. Future advancements, like developing ultra-strong materials, may eventually aid in addressing these issues, but climbing a tether from the ISS remains unfeasible today. This concludes our examination of the topic, clearly showing the complexities and future potential paths in space tether concepts.